Your product is going to be Markovnikov. So what does it mean, Markovnikov? What does Markovnikov addition means? The carbon with the less hydrogen gets the OH. The carbon with greater number of hydrogen would get the hydrogen. So the least substituted carbon would get the hydrogen. More substituted carbon would get OH. Or rich gets richer, so hydrogen is going to be added to the carbon with the more number of hydrogens. Is this addition a Syn addition or anti-addition? So anti-addition, what does anti-addition means? Anti-addition means you need to know the mechanism. Yes, you need to know the mechanism, but you have to get used to, because you have so many reactions, you have to get used to just based on name of the reaction. You need to understand, is it going to be Syn addition or anti-addition, or it doesn't apply to it. So when you add H is coming first, right? H will come in first, and then you get carbocation here. So you get a CH3, and then you get a CH plus and CH3. If you use this example, because I have a CH3 up here, if it's visible. Okay? As a CH3 attached to carbon. What does anti or Syn means? In anti-addition, if the hydrogen is added from this side, for anti-addition, OH is going to add to the other side. So that's anti. So if you have this relationship here, these two, this is the anti-relationship, anti-addition. Hydrogen is added from one side, OH is added from the other side. If you have Syn addition, for Syn addition, you get this relationship here. If the H is added in this carbon, if you add the H on this carbon, OH is going to add to the adjacent carbon from the same side. So this is the same side addition, and this is opposite side. But one to each carbon though. Hydrogen is added to one carbon, OH on the adjacent carbon. If it's on the same side, it's called the Syn addition. If it's on the opposite side, it's going to be anti-addition. And we also need to know if the addition is a Markovnikov addition or anti-Markovnikov addition. Addition of HBr. What type of addition is when you're adding HBr to CC double bond? Markovnikov or anti-Markovnikov? It's Markovnikov addition. Okay. In Markovnikov addition, H is added to one and Br is added to the other one, and Br in this case is going to be more substituted, added to the more substituted carbon. So it's a Markovnikov addition. Now, is the addition, is it Syn or anti? First, as you said earlier, we need to know the mechanism for the reaction. So what we need to know, what is the intermediate? And based on the structure for intermediate, we can decide, is it going to be Syn addition or anti-addition? So there are a couple reactions you want to answer. First of all, what is your reactant? What's your product? What is your reagent? Okay, that's the reagent. Do you need a catalyst? You don't need a catalyst. And then the last question, the last two questions, is the reaction Markovnikov or not? And is the reaction syn or anti-reaction? So, syn or anti. How do we know if it's syn or anti? You have to look at the mechanism for the reaction. So if the mechanism for this reaction, it says you have carbocation, which way is the carbocation added? Would the carbocation add from the top or from the bottom? Would it make a difference? Okay, which one is going to be added then? Which side is going to be added from? On top. What is the hybridization for this carbon, which is carbocation? Hybridization for this carbocation is sp2 hybrid carbon. If it's sp2 hybrid carbon, and because it's sp2, your bromide ion, it can come from the top or can come from the bottom, either side. So the syn and anti addition is not going to make a difference in this case. So this is not applicable. We don't know if it's going to be syn or it's going to be mixture, basically. That's why for like substitution reaction, when you had the carbocation, because after you have the carbocation, then the reaction becomes the same as like SN1 reaction. So when you have the carbocation, your nucleophile can come from the top or the bottom, and since is like a 50-50 chance, or if you be more precise, it's going to be greater chance from the side that the empty or less chance for the side that leaving group is leaving, then you get mixture of two products. So in this case, you get a mixture of syn addition and anti-addition. So if you have mixture of two addition, then you need to know that when carbocation forms and there is no restriction, you see both sides is open, then we are going to look at the product. It could be syn or addition or the anti. So both syn and anti-addition for addition of HBr. Yes, when carbocation forms, okay, when carbocation forms is going to be both syn and anti-addition, because there is no restriction. If carbocation, you have to look at the structure for intermediate. Carbocation forms and there is no restriction. So it could go from the top or it could go from the bottom, and that would end up with syn or anti-addition. But the addition is going to be a Markovnikov addition. This reaction does not require a catalyst. Yes, you could say it depends on the formation of carbocation. Carbocation is always sp2 though. Carbocation is always sp2. Okay, now we have looked at addition of water, addition of HBr, addition of HBr with peroxide also. Addition of HBr with peroxide, we have carbon-carbon double bond. We are going to add the alkyl peroxide and HBr. And in this case, addition is going to be anti-addition. I'm sorry, anti-Markovnikov addition. So basically, Br is added to one carbon, and then H is added to the other carbon, but H is added to carbon with least number of hydrogens, and hydrogen is added to carbon with the greater number of hydrogen of the carbon-carbon double bond. So this is the anti-Markovnikov addition. Anti-Markovnikov addition. Is it going to be syn or is going to be anti-addition? This one is also both, because in this case you are going to get the you are going to get, when the Br comes in first, you will get the free radical. And for free radical, also you have a sp2 hybridization. So addition is going to be both syn plus anti-addition, both. That's for addition of HBr. Okay, so we probably have some reactions that is either syn 100% or anti 100%. So these are the reactions that it didn't make a difference. We didn't have to worry about it so far, but from now on you do have, you get some reactions that they are going to be either syn or anti-addition. Addition of Br2. What slide we were in? Bromination, yes. Addition of Br2 or bromination. Okay. Addition of Br2 or Cl2. Is the addition going to be syn or anti-addition? Then we have to look for the mechanism for this reaction. What do we have as intermediate? The first step of this reaction, in the first step of the reaction, the pi bond is going to come and form bond with the Br. So you have a Br here. When the pi bond comes in, is going to take the Br, with no electrons, and this electrons is going to break over the second bromide. So when Br comes in and does not bring any electrons, is going to consume the pair of electrons from carbon-carbon double bond in order to form the bond. So you're going to get a CH3, Br, and C plus charge here. You have a minus, and then you have a plus charge here. And because of this, plus and minus, these are too close to one another. And because it's too close to one another, right away there would be a bond forming between a Br minus and carbon cation. When that bond forms between the Br minus and this carbon cation, basically this is going to close a triangle. And when it does close a triangle, you are going to get a CH3 here, a Br attached here. So you get, when you get your Br, okay, when you get your Br, then you will get this structure because it's more clean. I'm going to show you this one. So you have a plus charge in the triangle area, in this triangle. So now the Br minus, which is acting as a nucleophile. So in this case, your electrophile, remember for addition, you had electrophile and you had a nucleophile. When you are adding water, electrophile is H plus, nucleophile is OH. When you are adding HBr, H is electrophile and Br is the nucleophile. When you are adding Br2, first Br is your electrophile because it's coming with no electron. The second Br is going to be your nucleophile. So when the nucleophile comes in, it has two choices to go from to the top in this where you have this part of the triangle, or it comes from the bottom when there is no restriction. Which one would be a better addition in this case? Should the Br come from the bottom or go from the top? From the bottom, definitely, right? Because there is no restriction from the bottom, but the top of this molecule now is restricted by the Br plus, by this triangle. When this triangle forms, or any time, So from now on, remember when I said when you have a peroxide, just know that anytime there is a peroxide in the reaction mixture as part of the reagents, either alkyl peroxide or hydrogen peroxide, your product is going to be anti-Markovnikov. So these are little pieces, not everything applied to the same reaction. In this case, you have a triangle. Anytime for your intermediate, if you have formation of a triangle, the addition is going to be anti-addition. So if the one BR is added from the top, the other BR must add from the bottom. So opposite side, so it's anti-coplanar addition. So it's going to add one from the top, one from the bottom. Is this addition Markovnikov or anti-Markovnikov? Addition of Br2, is it Markovnikov or anti-Markovnikov? Markovnikov or anti-Markovnikov? So when you say anti-Markovnikov, what does it actually mean? Anti-addition, meaning addition from the opposite side. Anti-Markovnikov has a different meaning, right? Would addition of Br2 be Markovnikov or anti-Markovnikov? Why is anti-Markovnikov? What does it mean if it's anti-Markovnikov? If you repeat the rule for Markovnikov addition, to the best that, okay, because there is no difference in the groups that bond to the carbon, then it's going to be not applicable. Perfect. So because you're adding Br to one carbon, you are adding Br to the other carbon. So Markovnikov and anti-Markovnikov is if you were adding hydrogen and you were adding Br, or if you were adding Br and you were adding OH, or if you were adding formation of the carbocation on one carbon, then it would make a difference, is going to be Markovnikov or anti-Markovnikov. In this case, you have, there's no difference. So since there is no difference, Markovnikov or anti-Markovnikov is not applicable when you are adding halogen. So it's just the halogen, so Br2, Cl2, you're adding the Markovnikov, anti-Markovnikov is not applicable. But syn or anti-addition, yes, it is applicable. What type of addition is this? Is it syn or anti-addition? It's going to be anti-addition. Markovnikov, anti-Markovnikov does not apply to addition of halogen. Okay. So the intermediate does not stay as a carbocation when you are adding Br. Br is not stable because of this plus charge that you have and the pair of unshared electrons you have on the bromine. These are too close and is going to form bond and is going to show as a triangle. Then you're adding the other Br from opposite side. Is going to be added from the opposite side. Now, if the CC double bond is not symmetrical, like this one, then there is a big difference that is going to, the Br plus is going to be more stable on which carbon. But in this case, it doesn't matter. For Cl2, same thing. A triangle is going to form, and when the triangle forms, then you have your second Cl coming and adding to the triangle. And what happens when the second Br comes in to add to the triangle? When the Br minus comes in to add to this triangle, count the number of bonds you have on the carbon. How many carbons you have? How many bonds you have on this carbon? Already, you have 2 hydrogens attached and 1 bromine carbon bromine, and then there would be 1 carbon bond. So you have 4 bonds already on this carbon. When the Br comes in to form bond with either one of them, is going to have to make the 5th bond, and a fifth bond on carbon is not stable. Just like negative charge on oxygen, fifth bond on carbon is very, very unstable. So what's going to happen? There is no pi bond to break here. There is no leaving group to leave. So what's going to happen? The weakest bond breaks. What is the weakest bond? The triangle is going to open. When the triangle open, remember with the triangle, like if you had cyclopropane, this bond angle here is a 60 degree, which is going through a lot of pressure, like angle strain, because if its open chain is going to be 109.5, and when it's restricted inside the triangle, or to form the triangle, it's going to be 60 degree, so it's going to easily open. So this is the weakest bond. The bond is going to break over the bromine when the new bond is coming to form. So carbon cannot have more than 4 bonds. If its new bond is forming, one of the old bond has to break, and that is the weakest bond that is breaking. So we do have two-step experiment here, reaction here. Step 1, formation of this triangle, and then step 2 is the formation of the product. So addition of Cl2. What is the purpose of adding methylene chloride in this reaction? The Br2 or Cl2 non-polar reagent, in order to bring in, you must keep it in the solvent. So methylene chloride is acting just as the solvent. Okay. What else do we have to discuss for the formation of the product? Is it going to be Markovnikov addition or anti-Markovnikov addition? Is it going to be Syn addition or anti-addition? Is it going to go through rearrangement or no rearrangement? If you look at this intermediate, there is no chance for rearrangement. So when the bromination takes place, there is no chance for rearrangement. When adding HBr, because carbocation forms that is not restricted carbocation like a triangle, there's a chance for rearrangement. So that's one of the disadvantages of reactions that you're like adding H2O with the acid catalyzed. There is a chance for rearrangement. Adding HBr, there is chance for rearrangement. So basically, in this case, there is no difference in the carbon skeleton. So carbon skeleton stays the same. Means that there is no chance for rearrangement. And methylene chloride is solvent, and there was no catalyst needed for the reaction. Okay, addition of halohydrate. Halo is part of the halogenation, and hydrine is part of the hydration. So for halogenation, you add Br2, and for hydration, you add H2O. When it comes to halohydrate, you're adding Br2 and H2O, both of them. Which one you're adding first is going to be the halogen, because when you bring the halogenation did not require catalyst, right? So you bring the halogenation first. So you add the halogen first, then you add water. When you add halogen, what would be the intermediate? A carbocation or twisted carbocation, or another word, just simply a triangle restricted carbocation. When you add the Br2, the first step is going to be formation of a restricted carbocation. So when you add the Br2, you get to the formation of the restricted carbocation. And the next step, when you are adding water, when you add the water, now for asymmetrical alkene, that means that the alkyl distribution is not the same on both sides of the carbon-carbon double bond. You have only hydrogens on the right side, alkyl group on the left side. Now, there is a plus charge inside this triangle, or this plus charge that is on the bromine. Is it going to be like moving around in this inside the triangle? Which element from the triangle can handle the plus charge the most? So if you have three choices, which one would be able to handle the triangle the most? If I call this one 1, bromine 2, and the other carbon 3, which element from this triangle can handle the plus charge the most? Bromine, carbon 1, or carbon 3? Definitely not bromine, right? Why not bromine? Because bromine, just like oxygen, has high electronegativity. So if it has high electronegativity, doesn't like the plus charge. So the plus charge that is here and this carbon and this bromine is not stable. The plus charge is not stable on bromine. Now, bromine out of the question. You take one, like we'll eliminate one of the three choices. Now you come down to two choices, 1 versus 3. Which one can handle the plus charge the best? In other words, the plus charge, is it going to be more stable on carbon 3, number 3, or is it going to be more stable on number 1? That's what you're looking for. So first you say no bromine, definitely. Then between number 1 and number 3, which one can take the plus charge better? Now, what side, the side that both of them, the fact that both of them is attached to bromine, that is equal. So we have to look for point of difference. The difference is number 3 is attached to 2 hydrogens. Number 1 is attached to 1 hydrogen and 1 methyl group. And since methyl groups are electron donors, then a plus charge on carbon 1 is going to be more welcome, or plus charge is going to be more stable when it's on carbon 1. So when you have a chance, or when on the next step, when you're bringing in the bromine, so the first step, just like adding Br2. So the first step, this triangle is going to form. So for the first step, this triangle with the plus charge inside the triangle is going to form. Next step, H2O is coming, and now H2O has two choices: to be attached to this carbon or to be attached to this carbon, the second carbon. Because H2O is coming as a nucleophile and is looking for the plus charge, so nucleophile looking for plus charge, and where the plus charge is going to stay or be more stable is going to be around the carbon 1 here, or carbon that is attached, more substituted carbon. So if it's attached to, then as a result, H2O is going to add to the more substituted carbon. When H2O comes in, because it doesn't have any negative charge, as a result, the plus charge that was once on the triangle now is going to move down to H2O. If it moves down to H2O, why is moving down to H2O? Because H2O came in as a nucleophile. It came to rescue that plus charge, so it's going to take over that plus charge. What is the problem in this step now? In a step like a second step or second compound that we have. What's the problem with this? With this structure that I called second. So I'm going to call this one first. The The plus charge on oxygen is very unstable. When plus charge is on OH2 or plus charge on water, there are two options. One of the options would be to remove water, which is not going to benefit. It's going to go back to carbocation. The second option would be to remove H plus. So when the H plus is removed, the plus charge with one of the hydrogen is removed. The net result for halohydrin, the net result for formation of halohydrin is addition of halogen and addition of OH. So when you are learning this addition of or halohydrin, formation of halohydrin, your reagent is going to be halogenation reagent, which is addition of Br, and hydration reagent. So this is your reagent. Addition is going to be anti-addition. And why is anti-addition? Because the intermediate that you have is going to be restricted by a triangle. If it's restricted by triangle, then addition is going to be anti-addition. Is it going to be Markovnikov or anti-Markovnikov? In this case, is the Markovnikov addition because OH is added to more substituted carbon. So OH will add to more substituted carbon. The addition is going to be anti-addition. If Br comes from one side, OH is going to attach from the opposite side. What happens to the other bromine? The other bromine is going to form the byproduct, because when you bring the H2O, you are only using the OH from H2O. You're bringing Br2 is going to use one of the Br, and the other one is going to form a HBr as a byproduct. So you get your byproduct, and your byproduct in this case, because it can change, it has a very low melting point or boiling point, and it can change the gas, it can escape the reaction mixture, is not going to cause much of a complication here. So it's going to be easily removed. So, but what happens to it is going to form the byproduct in the reaction. So the OH, just remember the OH would never be on the same carbon that you have the Br. It's not going to be on the same carbon. So it's either carbon 1 or carbon 2, but which carbon is going to be carbon is going to be more stable or better candidate for it is the one that carries or handles the plus charge easier. So this more substituted carbon, because it's more stable transition state or more stable, the plus charge is going to be more stable on that carbon, then the OH is going to add to the carbon that is more stable. So your electrophile in this case is going to be your halide, the Br is going to be your electrophile, and the nucleophile is going to be OH, because it's addition reaction. So you want to know what is the electrophile, what is the nucleophile. Okay, next reaction. So we talked about hydration, adding water directly with the acid catalyzed. We talked about halogenation, that means adding Br2, which we add Br to one carbon and Br to other carbon. We talked about H2O, H plus, that was the hydration that we talked, the Br2, and then we talked about Br2 H2O. So hydration, halogenation, halohydration, that means halogenation plus the hydration. And for each one of them, you need to know if the product is Markovnikov, anti-Markovnikov, or not applicable. Like in this case, it's not applicable. Is the addition, anti-addition, we also talked about the HBr, and the HBr with peroxide. So hydration, halogenation, halohydration, the addition of HBr directly, HBr is going to be directly, and then HBr anti-Markovnikov. So Markovnikov or addition of HBr with the peroxide. So halogens. So for the for halohydration, the Br is going to add, halogen is going to add to the least substituted, and OH will add to the most substituted. So if you count for the OH, what location OH is going to be attached, because it's attached to more substituted, you can classify this also as the Markovnikov addition. So halohydrate would be Markovnikov addition, because your electrophile, which is the Br, is going to add to the least substituted carbon, and your nucleophile is going to add to the most substituted carbon. So Markovnikov addition. If we take it to like just the hydrogen and Br, then it's a question. Well, you said the Br on the most substituted carbon, but if you take it like expand a little bit and say that is the electrophile versus the nucleophile, which carbon would take the electrophile, which carbon would take the nucleophile, then for formation of halogen, it's Markovnikov, and OH is going to add to more stable and more substituted carbon. Okay, so far we talked about 5 types of addition reaction. Like if you want to add the Cl2, addition of Cl2 is very similar, but it would classify under the same type of reaction. So addition of Cl2 or Br2, both of them is like halogenation. So these are the 5 types of reaction. You need to know what's your reactant, what's your reagent, what's your product, if there is a catalyst or there is no catalyst. We had catalyst when in this case, and addition of water. Next reaction, if we call the addition of water with the catalyst as a direct addition, direct hydration, then we also have 2 methods of indirect hydration. What is indirect hydration? Is like you're not just adding water with the acid catalyzed. So this is a direct reagent for direct hydration. There are other reagents involved in the reaction. So you get like intermediate with the different elements attached to it. And final addition, the final product is addition of water, addition of H and addition of OH. One of those indirect hydration, so this is the indirect hydration, is oxymercuration, demercuration. Oxymercuration, that's one step of the reaction, and then next step you're going to replace the mercury with hydrogen or reduction. So we call it like demercuration or reduction step of the reaction. Basically, you're bringing the mercury to attach to carbon-carbon double bond first, and then you are going to remove that mercury by bringing reducing agent of sodium borohydride. What is sodium borohydride? Sodium borohydride is a compound that can provide H-. It can provide hydride ion. And if you can have hydride to a carbon, basically you have reduced that carbon. In organic chemistry, oxidation meaning adding oxygen, reduction means adding hydrogen. So oxidation is adding oxygen, reduction meaning adding hydrogen. So sodium borohydride is a reducing agent because it can add hydride. So it must add either H2, 2 hydrogens, or add H with a negative charge. In either case, it's called addition of is a reduction reaction, reduction type reaction. When you're adding H2O, it doesn't count as reduction or oxidation because you add one oxygen, that's oxidation, you add two hydrogen, that's reduction, then is going to cancel each other's effect. So one oxidation, one reduction taking place at the same time, so it's neither. So hydration is not oxidation or reduction, but addition of H minus is reduction, addition of oxygen is oxidation. Okay, what happens in when you bring in in this indirect hydration? Oxymercuration, demercuration. What is your reagent? The reagent that you are going to bring in is going to be mercury 2 acetate, OAC2. Acetate, OAC, stands for the acetate ion, is same as CH3COO minus. So abbreviation for acetate ion is OAC. So when you say mercury and 2 acetate ion, the mercury, the charge for mercury must be 2 plus. So 2 plus charge on mercury and then 1 negative charge on each acetate is going to cancel each other. So you have mercury 2 acetate. One of the explanation for this reaction was that you get your mercury 2 or mercuric acetate. When you say mercuric acetate, going back to general reaction, when you say mercuric, that's for higher oxidation number. Mercurous is going to be Hg1 plus. Mercuric is the Hg2 plus. It's going to self-dissociate. That's one of the explanation, and then the mechanism you're going to learn about everything and then say that is not clear or has not been proven. But this was one of the proposed mechanisms that in the first step, mercury 2 acetate is going to dissociate, is going to lose one of the acetate ion, and if it does lose one of the acetate ion, it's going to change to HgOAC. What's the charge of this? This is going, the acetate is going to be negative, right? What's the charge of this piece up here? This piece, what's the charge? It's going to be positive. So we have this positive charge generated. When you have that positive charge, this part of the dissociation, the product of the first step or dissociation of mercury to acetate, now it can act as the electrophile. And that's what we need in addition reaction to carbon-carbon double bond. We need an electrophile and then we need a nucleophile. So the mercury acetate ion, which is the HgOAC plus, it can act as electrophile in this case. Okay. In this reaction, what is the advantage? Why do we have to, we already knew about the hydration of water. Why do we have to do indirect hydration? What was disadvantage of direct hydration? In direct hydration, you would get a carbocation that is not restricted, the chance for rearrangement. For indirect hydration, when you do oxymercuration, demercuration, there is no chance for rearrangement, and I will show you the mechanism to see why there is no chance for rearrangement. So basically, what's going to happen, this electrophile, when it comes in, is going to basically form a triangle. When that triangle is formed, as the HgOAC, like a mercury acetate ion, is going to attach. And because of the intermediate that is triangle, then there is no rearrangement. The other advantage is that it doesn't require acidic condition. And the acidic condition, when you are adding acidic or basic condition, it could be harmful to organic compounds. So in this case, you're not adding the sulfuric acid. So sulfuric acid, what it does, it can easily dehydrate the organic molecule. So it could be harmful. So when oxymercuration, demercuration takes place, you don't have to add the acid catalyst either. There is no carbocation, so there is no rearrangement. So these are the advantages of oxymercuration, demercuration. Two-step reaction. Step 1 is oxymercuration. Step 2 is demercuration. Okay, the mechanism that is explained in this slide is slightly different from what I said, but believe me, the other one is also valid, or both of them are not very clear, so they are both on the same boat, basically same level. So you can say that you could use either this one, this mechanism here, or what I proposed in the previous slide, and I said that HgOAC would generate first with the plus charge, and that acts as the electrophile, or you could say that mercury 2 acetate is going to be attacked by the pi bond, and then the leaving group is going to leave. But this is the net result. But if you say this is going to form first and is going to attack or form bond with the carbon-carbon double bond, it's also it is valid because there are books that actually explains this way. When the mercury acetate ion comes in and forms the triangle, see, when you see the triangle, what's the first thing it comes to your mind? How formation of triangle affects the product based on it's going to be anti-addition. Very good. What's the advantage of formation of this triangle? Is that there is no chance for changing carbon skeleton either. So carbon skeleton doesn't change. There is no rearrangement. So there are two things should come to your mind. First, the addition is going to be anti-addition. Second, there is no chance for rearrangement. So when this triangle forms, at the next step, you are going to get water being added as the nucleophile. When water is added as a nucleophile, which carbon would take the water? So basically the question comes in, on which carbon the plus charge be more stable, because this plus charge that is here, now it can be shared between mercury, the CH2 and CH. So which one would take the plus charge easier? CH. CH would take the plus charge easier because CH is attached to another alkyl group, which is electron donor. So H2O is going to attack this CH bond and form bond with the CH. The plus charge comes in, the triangle is going to break. So these movements has to be like automatic in your brain, in your mind. When the triangle forms with the plus charge, when H2O comes in, H2O doesn't bring a negative charge. So when H2O comes in, it's going to take over that plus charge, or is going to comfort that plus charge because it's acting as a nucleophile now. That plus charge on the oxygen, then what should come right away to your mind that, okay, I see a flag here, the plus charge on oxygen is not stable. What should I do next? I have to remove one hydrogen with the plus charge. So if you remove the hydrogen with the plus charge, now you end up with the OH. So what have you added to this carbon-carbon double bond so far in this step of reaction? Is this a product or is it intermediate? There is no plus charge because this is a byproduct. That's not part of it, okay? So we're just talking about if this is a product or is it intermediate. I can call this as a product because there is no plus charge, no minus charge. This is not intermediate. So the first step of this reaction you are getting oxymercuration. What does it mean? Mercury is added to one carbon and oxy is added to another carbon. So addition is anti-addition. This is still one step of the two-step reactions. In the first step, your product is oxymercuration. You're adding mercury and you're adding oxygen or OH to this molecule. That's not addition of water. Well, what is addition of water? Addition of water is adding H and addition of OH. In the first step, all you have done, you've added the OH already. Now, in order to complete your hydration, which is addition of H and OH, you have to replace this with H. And to replace that with H, what would be your reagent? To replace this with the H, the reagent that you are using is your reducing agent of sodium borohydride. So when you bring in sodium borohydride, and the next step of the reaction is going to replace the H with mercury. So it would remove the mercury and add H to this carbon. The net result is going to be addition of OH, addition of H. Is this addition Markovnikov or anti-Markovnikov? Is the addition Markovnikov or anti-Markovnikov? If you look at the steps of the reaction, in this step of the reaction, OH is going to be added to the more substituted carbon, and this step of the rhythm is going to say that your addition is going to be Markovnikov addition. So the addition is Markovnikov addition because in one of the steps of the reaction, when you bring the nucleophile of H2O, it's going to be more stable if it's added to more substituted carbon. And that is the part that is going to end up with the OH. So OH is added to more substituted carbon. That's definition for anti-Markovnikov, Markovnikov addition. So this is the Markovnikov addition. Because later on, we are going to, okay, very good question. When you say carbon with most hydrogen, carbon with the least hydrogen, which carbons are you comparing? You are only comparing carbon A and carbon B. Are you going to look at this? No. You're not going to look at the CH3. You're looking at CH and you're looking at CH2. CH has less number of hydrogens. That's the one that's taking the OH. CH2, for now, on this slide, you see the mercury, but I said that when we add sodium borohydride, this is going to be replaced by hydrogen. So the carbon CH2 takes hydrogen, CH takes OH, and this addition is going to be Markovnikov addition. Now, this addition is Markovnikov. Is it Syn addition or anti-addition or not applicable? Now, in the actual product is going to in the actual product, the Hg is going to change with the hydrogen. So the final product, you will get a hydrogen. One more time, is it Syn addition or anti-addition? Or not applicable? Is there any restriction to make this anti-addition or Syn addition? Any restriction? You have the triangle. Yes. Anytime, remember I said anytime you have a triangle as the intermediate, the addition is going to be anti-addition. Anytime you have peroxide the addition is going to be anti-Markovnikov addition. These are the hints. These are not the rules, but these are the hints. Whenever you have a triangle, the addition is going to be anti-addition. Whenever you have a peroxide in the reagent mixture, the addition is going to be anti-Markovnikov addition. Okay, next step. So you understand, you follow the mechanism for so far for the first step, which is the oxymercuration step of the alkene. The mercury acetate is going to act as a electrophile. It forms the triangle. Water comes in as a nucleophile, would attach to the most substituted carbon. Then you get the protonated OH or protonated alcohol here. You have to remove the H plus because the oxygen cannot handle the plus charge. So you have to remove that H plus. And your product in this step is called, step 1 is called Oxymercuration product. Next step, when you bring in the sodium borohydride, is going to remove He and add hydrogen. So it's going to do demercuration, basically. And remember, I said that the mechanism is not clear, or the mechanism was presented in this book was different from the other sources, that sometimes they just say that Hg OHC forms first, and then this is acting as the electrophile. So what you need to know from the demercuration part or reduction part, that hydrogen is going to replace the mercury acetate ion. So you have 2 hydrogens here, it changes to 3 hydrogens. So step 2 of the reaction. And memorizing the reagents is going to be your responsibility. You have to memorize those reagents. You have to know that. Oxymercuration reaction yields the same product as with acid catalyzed addition of water. Okay. Because it's also a Markovnikov addition. And the net result is addition of H and OH. You add hydrogen and you add OH. That's hydration, just like the acid catalyzed or adding H2O with H+. And it's a Markovnikov addition. Okay, which carbon is going to take H and which one is going to take OH? More substitute carbon, least substitute carbon, okay. Least substitute carbon, which is B, is going to take H, and the more substitute carbon would take the OH. Now, instead of adding H2O as the solvent, as the nucleophile, if you add alcohol, what would be your product? This is a new reaction, okay? It's a different reaction. You don't get alcohol anymore. You would get ether as the product. So you get ether as product. How you get ether? If you add alcohol instead of water in oxymercuration, yes. Addition of H and addition of OR. Very good, very good. So you have addition of H and addition of OR. So basically, the net result is addition of alcohol. So when you are adding alcohol, H is going to add to least substituted, and the OR will add to the more substituted carbon, and the product is going to be ether. Hydration, reaction of hydration or hydration, the result is alcohol, but in alkoxy migration, demercuration, is the product is ether. I'm sorry, I lost the last question. Let me do this. So alcohol as a reactant results in ether as a product. Alcohol is the product of hydration, addition of water. Ether is the product of addition of alcohol. So this reaction, let me bring it back to, but it doesn't have both of them in one place. So if you have a reaction, let's say you have, instead of this, you add Hg, OAC, 2, and you add H2O. You add H2O, and this is one step. And 2, you add sodium borohydride. What would be your product in this case? Your product is going to be OH and H. And the CH3 would stay. So when you're adding water with the oxymercuration, demercuration, your product is going to be alcohol. When you're adding alcohol, so if you add water, it's the addition of H and OH, which is alcohol. When you're adding alcohol, addition is H and OR, which the product is ether. So it depends on you're adding alcohol or you're adding water. So addition of alcohol to carbon-carbon double bond would give you ether. But for oxymercuration, demercuration, that's the difference is that when you do alkoxymercuration, you will get no rearrangement of carbocation either. So it's more specific product that you are getting. So you have to use more steps. It's not as easy as direct hydration, but there is benefit to it. The benefit is that you don't get the damage of the reactants from sulfuric acid that you're adding. That's one benefit, and the other benefit is that you are not going to get carbocation rearrangement. Okay, questions? Any questions? Okay. So, how many reactions you know so far? Too many of them, right? Too many reactions. Alkoxymercuration is the same as oxymercuration. Same mechanism as oxymercuration. So first, mercury acetate is going to come in, or that anion could be different anion, but acetate is the most popular. Would come in, it forms a triangle. Then alcohol comes in. When alcohol comes in, then you have to, when the alcohol comes in, so let me try the mechanism. So basically is going to be formation of the triangle first, okay, with the plus charge. Then the alcohol comes in. When the alcohol comes in, is going to attach to the carbon that is more substituted, sorry, is going to attach to this, but from the opposite end, from the opposite side, is going to attach to the carbon that is more substituted, because this plus charge is more stable on the carbon that is more substituted. Then you have, when you bring the alcohol, you're actually bringing plus charge in, because there was no negative charge on alcohol to cancel the plus charge. As a result, you will get that O attached to the carbon with the H with the plus charge, you are going to remove the H plus to make the alcohol more stable. Let me write the mechanism, and we are on slide 35, so I can come back to this. Somehow I didn't insert blank slides. I did for the other PowerPoints, and this one doesn't have the blank slides. I have to go back and forth, sorry. So let's say you have that and you're adding Hg, OAC2, CH3OH. That's one. And a second step is you're adding sodium borohydride. So what's the first thing that is going to happen? In this case, He, we're just going to write on the side that HgOAC. This kind of makes sense more to me, so I'm going to follow this mechanism. HgOAC with the positive charge. You have the mercury acetate, but what is positive charge? Because one of the OAC with the negative charge left, plus the OAC negative. This is our electrophile. Electrophile is going to be forming bond with the carbon-carbon double bond. So what we get as the intermediate, we are going to get a triangle here. The plus charges. And the next step, you are bringing your CH3OH pairs of unshared electron. This is going to come in, and when it comes in, has two choice, A choice, B choice. Which one is more? Which one is going to happen? Attack to A or B of the nucleophile? Would alcohol would form bond with the carbon 1 or 2? A or B? B. Okay. So when it forms bond with B, here's what you are going to get from anti-position, right? You will get the O, H, CH3, but there's a plus charge here. And then this carbon is going to get the Hg, OAC. Because when this forms, so this is not going to happen. This is going to happen, and when that happens, you have to show that this bond is going to break over the Hg. The triangle is going to break. So nucleophilic attack, breaking of the triangle. You get this. Still is intermediate. It's not a product. How is going to change the product after you remove the H and the plus charge? So when you remove this, how are you going to remove that? You bring another solvent molecule. So if you bring this, it's going to remove the hydrogen with the plus charge. As a result, you're going to have a product. And this product is called OCH3. And you have the HgOAC. Alkoxy Migration. That's the first step. What happens on the second step? On the second step, you are going to bring in sodium borohydride and ABH4. You bring sodium borohydride. What the sodium borohydride is going to do is going to reduce this molecule. What is the reduction? What is the net result of reduction? Placing this group with H. So you will end up with H added to carbon 1 and O CH3 added to carbon 2. This is your final product. Okay? That's the final product. What is the net result? The net result is addition of H and OR. The functional group is ether. So what you added alcohol with alkoxy, with the alkoxy migration demercuration. So basically it's addition of alcohol to carbon-carbon double bond. H is going to add to this carbon with the least number of hydrogen. The OR is going to add to the other carbon with the greater number of hydrogen. So you have your alkoxy migration demercuration. If it was water or oxymercuration demercuration, the only difference is that here you have H2O. And then H2O here, OH, and you end up with OH and H, addition of H and OH. So it's addition of H and OH when you are adding water, you get alcohol. Addition of H and OR when you are adding alcohol, your final product is going to be ether. What was the slide number I said we were on? 35? We were at slide number 35. Yes, okay, thank you. Okay. So alkoxy migration demercuration, the product of ether. And moving to next reaction. What is next reaction? Formation of epoxide or reaction of peroxy acid. Peroxy acid. What is the word peroxy or peroxide? Peroxide is a OO with 2 negative charge. Basically, this is oxide. That's oxide. And O2 with 2 negative charge. This is peroxide. Okay. Peroxide. When you have hydrogen peroxide, basically that's what you have. You have an O2 with 2 negative charge, and then you make it bond with 2 hydrogen to cancel it or to neutralize it. Is peroxide stable or not stable? Peroxide is unstable. It's not stable. Very good. Now, it's going to decompose, right? If you leave the bottle of peroxide, hydrogen peroxide, exposed to light or heat, is going to decompose. What is the product of decomposition of hydrogen peroxide? It will give you water and H and oxygen, right? So basically, peroxide is going to change to oxide. And this one is a lot more stable. Water with O2 is a lot more stable than the hydrogen peroxide. So carboxylic acid, functional group for carboxylic acid is a COOH. When you say peroxy acid is COOH. I call this A and B. Stable. A or B? Stable. What do we have here? OO, single bond, that is peroxide. So whenever, the reason I brought the hydrogen peroxide, because everyone knows to hold the peroxide bottle. When you buy it, it says keep it away from light and heat, right? Why? Because you don't want it to get it, you don't want to get it decomposed. So it can decompose on its own. Over the time, it will decompose even if you keep it dark, in dark place. So peroxides are not stable. Oxide is stable. Proxy acid is not stable. Carboxylic acid is stable. So if you use this as a reactant, is dying to go to form the carboxylic acid. How could this proxy acid, so this is the proxy acid, how could it go to the carboxylic acid? It has to lose one oxygen, right? It has to lose one oxygen in order to go to minus one oxygen, it will go to carboxylic acid. And this, it's just when you look at the proxy acid, or if you see CH3, CHCOO3, something is a close. So if you see like a RCO2H, that's carboxylic acid. But if you see RCO3H, it should just raise the flag that this must be a very unstable compound. CO3H, it actually exists. It's not a typo. What is this? That is the proxy acid. So when you have a proxy acid, in order to change it is this bond, because it's very weak. And the good example was from the hydrogen peroxide, because it decomposed on its own. That's why is a weak bond. It's going to break. And in order to change to carboxylic acid, it must lose one oxygen. So this is a good candidate, good oxidizing agent whenever you need one oxygen. When you need just one oxygen to use from the molecule, to remove the oxygen from the molecule, this reagent is a good candidate, because by removing oxygen from this compound, this reactant, this compound is going to change to a more stable compound. When you have like one oxygen here you have peroxide or proxy, here you have oxy. It would change with this hyper going to more stable. So what is that's one thing you need to know, that peroxide are very unstable, oxide is more stable. When you have an OO single bond is unstable, so this is unstable, it can go to carboxylic acid. The other thing you need to know that what is epoxide? Definition for epoxide is a triangle, a three-member ring, that one of them is oxygen, is one oxygen and two carbon. So now epoxide using proxy acid. You start with the carbon-carbon double bond, you add epoxide. Basically, this is dying to lose one oxygen. This oxygen is going to come in and form a triangle between two carbon from the carbon-carbon double bond. So your net result is formation of epoxide. What's your reactant is alkene. What's your reagent is a proxy acid. And what's the product is epoxide. Then carboxylic acid is going to be your byproduct. Sometimes we don't even write down the byproducts. It's kind of understood that it's going to be there. It needs to be purified, but we don't have to write it always. Okay, so we have the alkene plus peroxide that gives you epoxide and carboxylic acid. Is the addition Syn addition, anti-addition? Is the addition Markovnikov addition, anti-Markovnikov addition? Not applicable. What is the addition? Basically, Markovnikov and anti-Markovnikov is not applicable because you're only adding one oxygen. You're not adding the electrophile and nucleophile, and you isolate this as a product, right? So you're not adding H and OH, you're just adding oxygen. So addition is not going to be Markovnikov, neither anti-Markovnikov. Is the addition Syn or anti-addition or anti-addition? That also is not applicable. Why is not applicable? Because you're just adding one element. If you were adding a second element, then it would have been anti-addition because of this triangle. But if it's just addition of oxygen, it's not applicable. So for this reaction specifically, and Markovnikov, anti-Markovnikov, not applicable. Syn or anti-addition, not applicable. If you were continuing this reaction by bringing a second reagent, then yes, you're talking about Markovnikov, anti-Markovnikov. But at this step, because you have a product, there's no plus minus charge here. This is a product, and it will stay with not applicable. Syn or anti or either one of them. Okay, do we have any questions so far? Hydroboration oxidation, that's another method for hydration or indirect method of hydration. And what you need to know, it's the reagent that you're adding. What's your reagent? What is the final product? BH3 is classified as electrophile. It's classified as electrophile because is electron deficient. Borane has Lewis structure of this. That's the Lewis structure for borane. Empty orbital. The octet is not satisfied, is looking for electron, and because it's looking for electron, is defined as electrophile. Because is electron acceptor, is also defined as Lewis acid. So is a Lewis acid that is acting for electrophile, is acting as an electrophile. And when you have a carbon-carbon double bond, you can bring this in first as the electrophile. Then you have to bring a nucleophile to continue for addition reaction. A set of reagents. That's what you need to memorize. For hydroboration oxidation, it's called hydroboration oxidation. So you're adding borane, you're adding water, and then you are oxidizing. So hydro, adding water, borane, you're adding BH3, oxidation, then you have to oxidize it. The net result is addition of water, H and OH. The addition in this case is going to be anti-Markovnikov. How do I know is anti-Markovnikov? How you should know is anti-Markovnikov already. Is there any hints in this reaction that is telling me this reaction is going to give me anti-Markovnikov product? Because I just said this is anti-Markovnikov, but how would I know that is anti-Markovnikov? By looking at this reaction without knowing the mechanism for the reaction. Is there a hint? I'm trying to make it easy for you. You look for hints to see if it's anti-Markovnikov or not. Remember, I said anytime you have a triangle, the addition is anti-addition. It comes from the opposite side. Anytime you have a peroxide, the addition is going to be anti-Markovnikov. You have a peroxide here, the addition is going to be anti-Markovnikov addition. There is no triangle here. That was just an example. You have to know it from mechanism of the reaction. When you do bromination or halogenation, a triangle forms, right? So the addition is anti-addition. When you have oxymercuration, demercuration, we know that triangle is going to form. This addition for hydroboration is not anti-addition or anti-addition, but it is anti-Markovnikov addition because of the presence of peroxide. As a hint, I said whenever you have peroxide, the addition is going to be anti-Markovnikov addition. So it's anti-Markovnikov, but we haven't talked about if it's anti or not because we don't know the mechanism, so we don't know that it's going to be anti-addition or not, but it's not anti-addition. Actually, this is a Syn addition. Both of them would add from the same site. Okay, so for direct hydration, you get Markovnikov addition. For hydroboration oxidation, you get anti-Markovnikov addition. So if you want to add the OH to carbon 1 or OH to the carbon with the greater number of hydrogen, then you have to use this reagent for anti-Markovnikov addition. So you want to make sure to bring the hydroboration oxidation. So we are adding borane, we are adding water, and we are adding oxidizing agent. H2O2 is the oxidizing agent. Sodium borohydride is a reducing agent. So in the first step, basically a bridge is going to form, and when the bridge is forming, you get the H added to one carbon, BH2 added to the other carbon, and then when you do oxidation, then you replace the BH2 with the OH actually. For the overall reaction, I'm going to cover the mechanism for this reaction, but not now because of the time. But with the overall reaction is formation of alcohol or addition of water. What's the difference between hydroboration, oxidation, and direct hydration? Direct hydration, you get Markovnikov product. For hydroboration, you get anti-Markovnikov. Oxymercuration, demercuration, you get Markovnikov product. Oxymercuration, demercuration, the addition is anti-addition. For hydroboration oxidation, the addition is Syn addition. And you learn that from the mechanism of the reaction. That's going to be a Syn addition. And I will cover the mechanism. I will go over the mechanism for tomorrow, but just know that the addition is going to be anti-Markovnikov addition. Basically, you're adding H and OH. H will be added to carbon with the least number of hydrogen, and OH will add to the carbon with the greater number of hydrogens. H is going to add to this carbon, and OH will add to the carbon with the greater number of hydrogen. This is known as the anti-Markovnikov addition. Would there be a rearrangement? No rearrangement. So that's another advantage of this over the direct hydration. If you just do direct hydration, you can make alcohol, but there is a problem with addition of acid. The acid can damage the organic compounds. The other problem is that there is chance for rearrangement. When you do hydroboration oxidation, there is no chance for rearrangement. When you do oxymercuration, demercuration, there is no chance for rearrangement either. Okay,